People often ask, what powers the chatbots we use every day? The ones that answer questions, write with us, debug code, or generate creative text. The truth is, behind every popular AI chatbot is a large language model built with design decisions, trade-offs, and capabilities that shape what it can and can't do. These models are usually transformer-based, pre-trained on massive datasets, and then fine-tuned or augmented so they can follow instructions, hold context, and behave more safely. When you open ChatGPT, that's the front end you see: the chat window, the message box, the conversation history. But behind it is a model from the GPT family, for example GPT-3.5, GPT-4, or newer. These are dense transformer models. Every parameter is active during inference. To make them conversational, OpenAI uses alignment training, reinforcement learning from human feedback, system prompts, safety filters, moderation, and layers of control to reduce unwanted behavior. When you use Claude by Anthropic, the interface is similar, a conversational chat UI. Claude is backed by Anthropic's transformer architecture, with extra emphasis on safety, caution, and consistency. Claude often declines to produce content in uncertain or risky scenarios more aggressively than some other models, favoring conservative outputs. When you talk to Grow-K by X, formerly Twitter, again you see a chat interface. Its model is tuned for fast, topical responses, often integrating more recent information or trending content. That gives it strength in freshness and immediacy, but can also make it more vulnerable to errors or hallucinations when live data is imperfect. Those are the user-facing names. What really determines behavior is architecture, data, and alignment design. A major recent shift is toward open-weight models whose full parameter weights are publicly released. OpenAI's release of GPT-OSS 120B and GPT-OSS 20B is a notable example. The 120B model uses a mixture of experts, MOE architecture, activating about 5.1 billion parameters per token. The 20B model activates around 3.6 billion per token. This sparsity reduces compute and memory demands. Because the weights are open, developers can run, fine-tune, inspect, or adapt them locally, something not possible with fully closed models. OpenAI's announcement of GPT-OSS outlines these details. At the same time, Meta introduced Llama 4, which accepts multimodal inputs, text plus images, and uses a mixture of experts architecture. Two variants, Llama 4 Scout and Llama 4 Maverick, showcase different trade-offs. Scout is designed to be efficient, with 16 experts and support for very large context lengths, whereas Maverick uses 128 experts, a much larger total parameter pool, and targets more intensive tasks. Because of the MOE design, these models don't activate all parameters per token, only the subset most relevant. That lets them scale capacity without linearly scaling inference cost. These architectural choices, dense versus sparse, number of experts, how many parameters are active per token, context window size, multimodal support, make a huge difference. For example, the GPT-OSS models support long context windows and use quantization to improve efficiency. But no model is perfect. Powerful models require more memory, compute, and energy. Latency and hardware constraints matter. In MOE systems, routing overhead and load balancing can reduce efficiency. Models trained on benchmarks often struggle in real-world, noisy, or adversarial environments. Hallucinations, confidently asserting false statements, persist. Bias is still baked in. Models tend to reproduce or amplify training data biases. And even in open-weight models, interpreting why a model made a specific decision remains extremely difficult. In one recent evaluation, is GPT-OSS good? A comprehensive evaluation of OpenAI's latest open-source models, researchers compared GPT-OSS 120B and GPT-OSS 20B across benchmarks like coding tasks, general knowledge, math, and conversation. Surprisingly, the smaller 20B model often outperformed the 120B variant in benchmarks, suggesting that more total parameters do not always translate to better results in sparse architectures. In the MOE domain, there's active research into expert granularity and routing strategies. One paper, The power of fine-grained experts. Granularity boosts expressivity in mixture of experts. Argues that increasing the fineness of expert subdivisions can lead to exponential gains in expressivity. So what should you, as a user or developer, keep in mind? First, choose a model suited to your needs. Text-only, multimodal, heavy reasoning, etc. Make sure your hardware can support inference demands. Benchmark error and bias across demographic groups and real input noise. Use alignment, filters, tool chaining, verification modules to reduce hallucinations or unsafe outputs. Maintain logging, fallback strategies, and human oversight, especially in high-stakes settings. Update models over time and monitor for drift or new failure modes. And value openness. Models that can be inspected, critiqued, and improved tend to be more robust. When you interact with ChatGPT, Claude, or Grok, you see a carefully engineered front end. But what you experience, the quality, behavior, mistakes, strengths, comes from architecture, data, alignment, and design trade-offs in the underlying model. The move toward open-weight models like GPT-OSS and innovations like Llama 4's MoE structure are pushing us toward systems that are more efficient, inspectable, and capable on modest hardware, not just bigger for its own sake. These models are powerful tools, impressive, yet imperfect. Understanding their architecture, limitations, and trade-offs is key to demanding better systems, deploying responsibly, and setting realistic expectations. Because as users, builders, or policymakers, we're not just using these models, we're shaping what norms of safety, accountability, and fairness will look like. Thank you for listening. Please like, share, subscribe, and comment.